Hello there, scientists and engineers, old and young. The Energy Physics LLC, making the second of our documentary model rocket series. First one was on boost glider competition with the NAR National Rocket Contest. These are my personal interests. Basically documenting these videos for educational purposes and to help others learn and get up the learning curve quicker where there's a limit or lack of information available to proceed and cover some of the more advanced engineering topics and concepts in both modern rocketry, Space 2.0, model rocketry, drone science, rover science. Basically, I've got about 97 projects. So this is the model rocket versions of these documented series. This one is going to focus on the American Rocket Challenge TARC. It's primarily targeting high school, middle school, and high school students in order to advance their science skills. And the primary purpose of it is to provide these opportunities to kids of all ages and all backgrounds so that they can obtain a passion, much as us many years ago were pursued on our own. Schools didn't have programs like they do now to help young budding engineers and scientists in the science classes unless you had a really good science teacher. All you had was the science fair contest. So I'm going to review what I think is the most helpful set of documents to help TARC students obtain the things that we probably didn't have when I entered science contests back in 1973, 74, and 75 in my own high school years. Amazingly, I usually won third place to second place and even first place in the Virginia Junior Academy of Sciences, which got me introduced to the University of Virginia aerospace engineers professors, Dr. Fred Lutz. Here at University of Virginia, Fred Lutz was at Virginia Tech, and I ended up going to Tech to pursue an aerospace and ocean engineering degree. From there, went into the military, became a military pilot, and through the years have never lost my passion for rocketry or for engineering, trying to get work in the space program. I'm not going to retire. That's just a passion. One of the ways I'm meeting that is to try to help TARC programs and provide assistance. I'm a member of the Northern Virginia Association of Rocketry, NOVAR, Section 205. I also have a AR certificate, which is number 55242, I think. So I got enough background and hopefully enough experience to help others get up this learning. So let's proceed with this introduction. I want to start in with a series of slides specifically focused on three phases. The first phase will be the design phase for TARC. I'm going to go through that series as fast as possible because there's a... So let's just introduce this slideshow. Everything is done in a slideshow to make it quicker, more easy to talk to. Well, TARC started way back, I think in 2009. It's now 2022. And typically now here at Northern Virginia, we fly them at Great Meadows, although we held them at 10 different locations around the country. Thanks to the tremendously hard work of Trip Barber, who is the inventor and the originator of the TARC system. He's an incredible MIT graduate officer who has dedicated his life to helping all of us, keeping our club going and helping all of us share information. And he's very talented at rocket contests. He's one of the people that speak with the detailed knowledge he has of how to win these rocket contests. Every year, he goes to NARM, almost everyone. He was in MIT back in probably, I think, 1977. But you owe what you're getting ready to get into to Trip Barber. If you see him out there, give him a thank you. And club members all appreciate everything. congratulations or service that we do, because we enjoy helping anyone learn science and the mathematics, rocketry. So this series is again designed to get you quickly through the process if you're a beginning team. If you're an experienced team, some of this will be redundant to you, but I think I can add some things in there that will inspire you to go beyond what is currently there, give you some ideas and some concepts that you may not have experience with. So the first thing that I recommend is you understand the basics of why you're doing this. The primary goal, in my opinion, for TARC is to get you to understand a process that is very similar to the way that you're going to need to operate out in a real job. You're going to have to do some research on things that you've never done before. You're going to have to work in teams with people that you may not have ever worked with before. You're going to have to get along in such a way that everyone compartmentalizes and adds to the basic knowledge and skill level of the entire team. The whole will do better than just one or two individuals working in isolation. That's the theory. And the primary purpose of TARC is not to just win this contest, although that's a great thing and you get some great prizes, but it's to bring you into a world of how to work in an environment that's going to be very similar to the skills and things that you're going to, experiences that you're going to want to have as you progress from middle school to high school to college and design your goals for what do you want to do. The TARC hopefully will set you up for a passion for some of that being in science technology, even whether it's educational or in the rocket industry. Country needs talented people, and basically helping you get along with people of all ages and respect and admire the great skills and work that people of all ages and all types. So TARC is really a goal of process and education, and not so much about winning, although winning is fun. But each of the teams that we talk with, they seem to enjoy the experience of just working with the environment of TARC. It becomes very exciting. And so the first thing I'd recommend is you start a project folder, put a bunch of your stuff into PowerPoint slides and take lots of videos, because you're going to want to do your marketing and presentation materials. So capture everything as you go along. Get started early. Again, that was all done in December. It's now March. So you should be just about flying, but in case you haven't, here's a review to go through and capability to improve your existing process. So phase one is the design. Here's the things you need to be aware of in terms of the constraints. Your rocket's going to have to be less than 650 grams. It's going to have to be greater than 650 millimeters in size, which is 5.6. Please use a metric system, because only two English metrics. So try to get rid of that. You can only use F-approved motors, typically 80 Newton seconds or less, and that's a safety issue and also a reliability issue. You purchase your engines already built, they'll be more reliable in the truck itself. And of course, we don't want you going out and experimenting with any of the chemistry stuff that typically graduate students or college students are trying to understand. That's under adult supervision. College professor and a college the skills necessary to get in, corporate type position. But we're getting you started here. Safety perspective, that's the only reason you're limited in terms of the motor size and reliability. Each year they try to do different types of challenges. This year you're going to use 2 different body tubes of 2 different diameters, which is unique. They have to be at least 150 millimeters or 6 inches long, both of them. You need to put in a 1010 rail button guide, and it can't be any higher than 6 feet off the ground when you launch. Total launch. You're going to be restricted with an altimeter payload, and that's simply because it makes it easier for everyone to have the same altimeter system. It makes it more fair. Plus, it's easier for the judges and the people that are helping to read the system without having to download flight data from. Again, you're going to carry eggs, but this time you're going to carry 2 of them. And the unique factor is they have to be horizontal this time, vertical. They can even lie side by side, but typically they're going to be a stacked system. And the constraint is it's no longer a 45 millimeter diameter this year. You're constrained by the length, which constrains you to a body tube, upper body tube of BT80 size, which is 66 millimeters. That 59 millimeters maximum inside of the body tube horizontally. So the length has to be between 56 and 59 millimeters, and your mass, which you measure, has to be between 55 and 60 grams. And the key is you need to protect it, typically with molded foam. Lon-D Component sells a nice horizontal kit now. And typically want to use a string mechanism to pull it out of the tube softly and gently so that you don't. The best part about this, in my opinion, is that they are permitting flight computers. Usually some of the best capabilities and most learning that's going on in TARC is systems that are being designed using flight computer systems. And I even see that there's a tendency for people to have more precision in their altitude and duration goals. And even the winners more often seem to be using flight computers and speed brakes controlled by those. So come up with some innovative stuff, and hopefully at least one member of your team will be a talented programmer and will understand the basics of flight computers and flight computer coding. Otherwise, you're going to have to teach yourself. But as a side note, it's not important, it's not critical to use flight computer in order to win. The winners typically in the past have used the standard tried and true methods of just doing repetitive launches and a little bit of luck involved. But over a period of time, you can start to nail those altitudes and durations closer and closer from a statistical perspective. In fact, learn some math and use some statistics to help you figure out whether you're converging on a good solution that'll help you win, or diverging, doing too many things, changing too many things without understanding the impact. Again, for safety reasons, there's no pyrotechnic ejections, typically what we call dual deployment or pyrotechnic black powder, again controlled by an altimeter or flight computer. Consider delayed release. I don't think that's allowed still. The Jolly Logic Shoot release is one of those systems. I'll have to check on that, but typically you're going to eject at the perigee maximum altitude with the minimum vertical velocity. That's, in my opinion, an area where your flight computers can start to really help because you're limited right now with the ejection charges of the motors. And at some point, I think the new precise solutions are going to be no longer relying on ejection charges of motors, but you're going to have servo type mechanisms that release the parachutes mechanically. And in my opinion, you should start thinking about those types of parachute release system designs controlled by flight computers that eject your parachute at the exact altitude. Exact speed brakes to slow yourself down. Your duration in descent goal is going to have to be 41 to 44 seconds. At the final event, there's 1 second less or more that they'll add. They'll change that so that it gives you a little bit of a challenge. The altitude goals are 554 meters, which and at final event, they're going to change that on you to 810 or 860 feet, which comes down to 246.8 meters, 268 meters. Calculator. That's an implied descent and a parachute constraint. So calculate yourself a vertical velocity indicator, and that's going to be somewhere between 6.195 meters per second, 5.77 meters per second. That's a hard landing. So figure out how to get some kind of a shock absorber system into your tube system to deal with that kind of landing speed that's over 5 meters per second is considered a hard. Parachute size will be determined by your burnout mass and vertical velocity indicator, especially if you have a flight computer board. And you typically use a timing target. Again, if you have a servo type parachute release, that's accurate. Otherwise, you rely on the ejection charge and calculate how many seconds of charge you need. Bounds it, but either too early or too late, typically because of the available engine. consider reefing your parachute as you dial the altitude in and you get the same distance to the ground. I'd recommend using 8 shroud lines, which give you best control, which is typically 1.5 times the diameter. This is always object for debate, and many NRM research papers on this. So look at the NRM websites to see what some of the previous researchers say about how many shrouds and what the length. That's a typical. So I'm going to base my TARC that I'm building, again, for educational purposes and demonstration purposes, off of a project that I did in 1974, school in my sophomore year, I think, in high school, and it was my year, and it was science fair. I think it took 3rd place, which was kind of fun. Helmut Dormut from Winchester, his design at the state. Anyway, that rocket was made out of paper towel rolls, and the adapter was hand carved so that I could get down to a BT-55 payload, which carried at that time a Transroc electronics receiver, which transmitted position rocket button. The state-of-the-art available, the equivalent of your flight computer today. Just we didn't have as much information, guidance, or teachers that could help us be mentors in how to do all that. Just kind of had to entirely do. So the second system that I based today's design on was the second one that I did of this series, the Transroc series, which the Echelon-D I designed in 5. And that was for a higher altitude, 25 millimeter, again carrying a Transroc payload. And I never built this because at the time I was entering Virginia Tech. 75 was my last high school. And so I took this information and pretty much computed rocket altitude calculation and did a whole series of calculations and mathematics that helped me hone my aerospace engineering, determine the drag, the CD coefficients, all that. Senior in high school, that's when I went to science fair. Modeling a spacecraft recovery. Again, I didn't have a lot of help except for my teacher, Mary Hayes, professor. Really encouraged me. So let's get up to date here. I would recommend that you first look at your overall constraints and put those into a modeling system. Either use Fusion 360, or I'd recommend that you use an online version of SolidWorks, which is OneShape. And then put your basic rocket components into that. And the reason you're going to do that is not only to get an assessment of how the components fit together and the sizes and shapes that you're going to use that will equate to stuff that you can buy as independent parts kit. But you may want to then PLA print a bunch of these components or laser cut these components once you're done. And this is the modeling system you're going to have in order to the 3D printing or the laser cutting possible. So go ahead and get your modeling done first. There are 2 ways to attack this problem. One is you could just go out and grab a bunch of kit material, throw it together with the basics of what you know, and go out and fly it right away. Iterate through that process, hit and miss until you get the right altitude and right engine selection. I would personally recommend that you can go ahead and do that right away. Just build one and just go fly it. But once you've done that and you've learned from those mistakes, hopefully you'll come back and realize that a design process is far more important. And that's a combination of your teammates sitting around and everybody brainstorming the best approach, and everyone learning how to model in OneShape system, as well as doing internet research that goes out and finds innovative designs out there that people have already done. One of the realities of working in a major corporation is that you can't possibly do it all over again by yourself. You got to go out and you got to do the research. You got to find other people's work, and you've got to understand that work. So that's where a significant amount of this concept called open source is extremely helpful to software developers and hardware designers out in the industry. Make no mistake that proprietary information, though it helps create financial capability for a company, it severely restricts the overall knowledge and ability of our country to progress. Using other people's work is very important with taking their starting point and improving on that. What you need, find the stuff that's already been done, learn how to do it, and whatever source you can find, educational material you can find, and improve on that. Do some innovative design that nobody else has done. That's the whole purpose of TARC, is how you build that, how you search it, how you do the research, how you put it all together, and then how you market it. Hopefully you'll understand this entire process in the end will lead to the best technology that you can develop that will help you nail altitude. That can be just building a standard system without any technical flight computer, just keeping the statistical records of getting the weight and balance correct, getting your mass ballast exact for the altitude and the type. So this is my version of TARC. You're typically going to see a lot of these very similar systems out there. It's going to be a BT-70 tube on the bottom. It'll either be trapezoidal or elliptical fins in most cases. You'll see engine retainer rings on the bottom, and it's a 29mm motor selection for most of them, although I'd recommend you also build a 24mm motor mount. Change them out. In fact, using the modular approach is very important. You can design systems that you can pull motors out and put new motors in with different sizes. And I recommend you take a look at building your system using modular components rather than just glue it all together. That's going to require some knowledge of the strength of materials and whether or not they fall apart. So learning how to put stuff that's replaceable takes another level of knowledge. And just remember that you got to carry those two eggs. They got to be protected. So the upper body tube is going to be a BT-80 as a minimum size. It can be bigger, and you can put them side by side horizontally. That's the only requirement, is they have to be horizontal. The next thing you should do is do a real quick simulation to test and determine your motor sizes. A typical tool for this that's free is called Open Rocket, and I recommend you download that. Also buy a commercial version of that from Aji Components called RockSim. But both systems, in my opinion, are extremely powerful and allow you to do basically everything you need to do. What size engines you need, what's your weight going to be, how long's the rocket, all these basic parameters that you can mix and match and change before you even do a single a bit of gluing or shaping or cutting or anything. Designing is really important at this stage to look at all your options, basically bound the kind of rocket you're. So you can see from this particular design, I've shortened the design components from the original that were in one shape model, just to see again how short and how small I could build one of these rockets. Again, I chose a 29mm tube and then another version, 24mm tube. And each of those required different engines and went to the same altitude, 254 meters. You just keep adjusting the mass balance that you put up front until you hit that altitude, and you hit those numbers in terms of durations, parachute sizes. It's just a modeling iteration process, typically. This is a printout of that to show basically your altitude, your vertical velocity, and your acceleration, and add other components based on what you're looking at, how much wind drift you have. And I make a recommendation that you look at wind. One of the key factors in loss of the TARC rockets is putting them up so high and then dealing with high winds, and then you lose sight of your rocket. It just goes out of sight and hangs up in the trees. So you need to calculate those wind drifts, and you need to estimate how far it's going to drift every launch. And you can use this simulation to do that. That way, you'll increase your chances of recovering financially, which is really a financial loss. It's not a safety issue as much as it's a loss and a loss of time. to not be able to recover rocket. This is another style that you'll see a lot. That has a bullet nose cone and even the soft TARC type nose cone. It's a foam nose cone to give it some cushioning, because the nose cone is going to be the first thing likely to hit the ground based on how you've set up your shot cord recovery. Also with a 29 millimeter, but a motor F27.4 is what turns out to be the type of motor needed to hit the exactly. And another picture of that altitude prediction. And then a couple changes. In this case, going down to a 24 millimeter motor makes it a little bit lighter and cheaper. So don't be hesitant to go down to a 24 millimeter design because you can get more launches. Motors are cheaper and they still reach the same altitudes and the same durations. So that's, again, a design decision that you and your whole team needs to make. Team meeting. So just one quick review. The last year was typically designs like this. They were all either BT70 tube sizes or they were all BT80 tube sizes. They tend to be two of the most popular. And they only had to carry one egg, and it was a vertical egg. And just want to caution you, don't order that vertical egg container from Haji Components. Make sure you get the horizontal one, new. So be careful about which one you won't get the wrong. These are the 2021 design parameters. Just go through them quickly. So let's talk about fins for a second. Basically, you can still use balsa as long as you strengthen it a little bit and you make a fit through the tube fin tab design. Probably going to need to have it somewhere between 3 millimeters and 4 millimeters in thickness. And you want to use either wood glues, which work real good with balsa and paper. And you can even use epoxy, which I would usually recommend, stronger material, especially if you change to fiberglass fin or you laser cut your fin. Attach them that. Typically, use a through the fin type of a design is better. It stands up to the motor stress. It'll last longer. And I usually make a recommendation to come out with innovative ways of making these fins removable. Again, removable component will allow you to replace broken parts, less stress on the rockets, carrying less components and quicker turnaround. And one of the ways to do that will be to PLA print a fin container or a fin can, typical, which is a smaller tube. Goes outside the body tube, and then you PLA print various fin holders and even pop rivet those things, or you cap nut screws, bolts, whatever you want to use as an attachment. Or again, you can just glue them and cut off any broken. These are your basic tube sizes. I've got a whole bunch of them listed, but you're using 66 millimeter BT80s or the 56 millimeter BT70s. The inside diameters are fit to the engines. The outside diameters, basically the thickness of the main issue is the engines themselves will determine the inside diameter, and that's a critical component for you. Once you have your designs and your simulations done, start sourcing out various body tubes, cost. Put all that into a list. Don't buy it right away, but just make a big list of all the stuff that you have, and make a source list of who can you buy it from and what's it going to cost. Again, you're going to have to do this with a real job, and like I said, the process is important. Put that in your marketing video and explain how you went through all that. That impresses the judges. They understand you're doing this as if you were doing a real job at SpaceX or ULA or any of the other Rocketdyne or Electron. So highly recommend you take a process, document and costs and your expenditures, how you ordered and who you ordered from. Body tubes are important because they determine the strength of the rocket. You can use fiberglass, but again, carbon board or phenolic tubes work just fine. Again, once you've decided on the overall design, go back and change your model so that you can do the CRC cutting or laser cutting of anything, especially motor mounts or tubes or capsules or special cut bulkheads that you can CRC later. Each of the couplers is important. It depends on how you want to separate your rocket, whether you have a solid coupler or an open coupler. Again, is a design decision to make. Considering that you only have a certain amount of ejection charge, and the longer that tube is, the harder it is to pressurize all that volume. But typically, a smaller rocket is better than a longer and higher volume rocket at an open tube. Another way to close that down is to use a solid tube coupler that you can purchase, or you can PLA print your own. I recommend, again, that you'll learn more if you learn to PLA print your own materials, do your own design. Typically, the rockets that are built by large level 1, level 2, level 3 rocket certifications are using hobby plywoods just for strength. But again, if you combine fiberglass and PLA together and a layered approach, you can typically get even better strength to ratios because plywood is englued, and so you can use carbon fiber and layer, or fiberglass and layer with epoxy. Put a thin layer of either plywood or foam or PLA printed material, whatever material layers you want to put up as you get more sophisticated in how you build these electronics bays, these couplers, your fins, and you can purchase these bulkhead designs. And I recommend that you take a look at piston ejection systems that prevent you from burning up your electronics. That's one way to do it. Again, another burn cloth, a Nomex cloth that you wrap around your parachute is another recovery system. So take a look at multiple ways of recovering the rocket and preventing the ejection charge from burning essential components, especially your, after a while, catastrophic burns and catastrophic failures occur. Things get heated up, and you'll find that your rocket will last maybe 10 to 15 launches before things start falling apart or breaking. Pretty common design issues, how to make them replaceable, and the parts are replaceable and the cheapest. And take a look at your engine tubes. Do a 29mm design tube, and the big issue is how do you want to do motor mounts or your centering rings. Again, you can PLA print those. You can use fiberglass. You can wood, plywood that's cut, CRC laser cut, all kinds. Or you can purchase them. Quickest way. Again, it's a decision you highly recommend that you use these engine retainers for most of the composite type tube engines. There'll be a little ring on the end of it, and or a little bulkhead that you just push up against it. You don't have to have an engine retainer on the inside, which is an older style design. Just make sure that you got a strong retainer on the outside of a composite engine typically, and then cover that with an engine that you typically want to purchase. Make sure the retainers match the tube sizes that you're using, the motor tubes, because they are slightly different depending on your source and thickness of the motor tube. Again, I recommend you take the extra time to design your own motor mounts and PLA print them. At that point, you can even put set screws in them or cap screws, and you can make them removable. Just make sure you do the stress testing and you do the ground testing in terms of how strong those are. Actually do a ground test of a real engine with your motor mount and see if it blows through. You don't want to have a blow through when you go out and do your first test and then it blows everything out of the pocket. Failure simply because your internal materials aren't strong enough, your glue wasn't strong enough, or the materials bonding that you bonded the inside of the body tube wasn't. This is a real problem when you go up through level 1, level 2, level 3 stations, these higher powered motors, and launch to thousands of. One of the reasons why we restrict you to level F motors, because the stress on the components is not as high and a lot more forgiving. If under design, under glue components, and this does, believe it or not, happen a lot. Some of the first launches that come up, they just blow apart or come apart. It's because of limited gluing or lack of knowledge how to build the interior components. Those kinds are fairly easy to model. I'll go real quick through a modeling process for you. The easiest I recommend is you go ahead and start with two lines that give the center and the radius of it, which in this case is a 66 millimeter diameter, outside diameter for your egg nose cone. And the inside diameter, not 19, it's a 64. And then use a spline tool and do that curve using little spline markers. Once you've got it set to a decent ogive type shape or elliptical or whatever shape you want the nose to be, then you revolve that around a center line using the revolve tool. Then you want to basically go through and extrude to sketch a second part, which is the back shoulder. You'll sketch that with a smaller diameter, typically go down to 63 millimeters and 1 millimeter size. Extrude that and then shell the inside of the whole nose cone once you consider it as a single part, using tool set to bring them together, shell out the middle to about 3 millimeters thickness, so the inside of it is hollow. And then typically when you hollow it out, you're going to have to put a hole the back side in order to about 10 millimeter penetration through that, so that the hole goes through and opens up into the cavity where the shell is. Don't do that. You won't see the shell open up. You can also buy your own polystyrene. It's a little heavier, but again, here weight, mass doesn't matter as long as you stay under 650 grams. So you can have a number of solutions that hit those altitudes of varying masses. You're going to use mass balance anyway. It's not critical to have the lightest possible mass components. Just whatever works best for you and whatever seems to build easiest to source. Or again, you're going down that learning curve of you want to build all your own stuff and PLA print all your own stuff and PLA print your own pins and everything. Go ahead and do that as a learning curve for the team. And it impresses the judges when you get the marketing video. Again, here's how we built it, here's the process, here's why we did it, in order everybody participated. Everybody had some skill set. You also have an option to get a foam nose cone. Again, this will help soften and cushion your egg. That comes with Apogee components. Sells for $10. So go ahead and try that if you. Or again, print your own on a PLA printer. I use a tool set called Ultimate Cura. There's 3 or 4 others that are out there, 3D slicers capabilities. Eventually get a G-code put onto a micro SD card, and that's what you're going to put into your. Do the fins as well. Not too hard to do. Just sketch that out using pins and lines and things like that, and extrude and fillet the fins as you finish them up. Then you can also 3D print those. You can get them into the model, or you can CRC laser cut them. What your approach is, and for that you need to turn that into a DXF type of a 2-dimensional drawing, AutoCAD type format, and use a tool called ArtWorks version 8, which is a typical CRC laser cutting tool that you could probably find at a local maker shop. Lucky enough to have a maker lab like Nova Labs, for example, Northern Virginia. Great place to use the university lab, but you'll have to sign up and be. Just ask your mentors or your schools where you can get access to. And this is the ArtWorks tool version of that to get the elliptical fin in. Then we set the laser cutting parameters, which is pretty much the speed and the engraving. The min powers are very essential. Min powers and max powers are set up based on the burn distance. That's all standardized and usually in a chart next to the CRC. For cutting all the way through plywood or different types of plastic. Just be careful that you don't cut plastics that cause dangerous toxic vapors. Very, very important consideration for laser cut is don't cut plastic. Typically it's acrylics. You want to consider using plastic rivets on your BT-80. Those are, instead of gluing everything, you'll be able to remove stuff a little easier and get to it. If you need to, do the same thing with your rail button designs. I'd highly recommend that you get rail buttons that are from the industry instead of make your own. The rail buttons buy are typically stronger and made out of better plastic. Add up all your rocket masses, do an analysis of your initial liftoff weights, masses, and then if you have time, put all that into MATLAB and Simulink and model your motors just to get a good set of printouts on the vibrations, the dynamics of the system. You do a lot with control theory. In this case, again, TARC is all about learning to use the tools that are used in real rockets. MATLAB and Simulink are very important control theory tools that you should probably learn to use at least by the time you get to college, but it doesn't hurt to start learning some of these concepts. Again, you're going to need at least one smart person in every group if you can, or learn this stuff yourself. Assign that task to an individual who has a high interest in control theory, and your entire team will benefit from going through that. Consider all different types of materials. You can ultracoats, monocoats that are typically used in airplanes, carbon fibers, glass epoxies, carbon sheets. Using epoxy, if you're going to build up your own fiberglass, you got to have peel ply and soft coats and absorbents for the excess epoxy, and you're going to have vacuum bag, good bubbleless design. Again, all kinds of ABS, PLA, PETG types of PLA printing materials. You're going to have your different drill guides and cutouts, different motors, and of course your horizontal egg payloads are going to be foam. I'd recommend always using M.3 3-meter mounting screws, maybe 3.5, but at least 3mm cap nut screws. With you can tap your own 3mm holes, tap and drill set, or possibly purchase little inserts melt down into the hot soldering iron. Again, you may consider plywood, you may consider foam surfaces. Foam is very lightweight, so some of that between two fiberglass or carbon fiber sheets. Form up the layers. And all of this is valid technology for building real rocket systems, and can't lose any points by doing this. You can't really gain any points by doing this, but what you'll gain is a lot of experience, a lot of techniques and science. Make the whole project more interesting, more technology. And the entire goal of TARC, get you motivated and get you learning new sciences that help you as you go in. The design tools that I'd recommend you using for your CAD, Onshape again, you can use AutoCAD 360, but Onshape is free, it's online, easy. You can use the 3D slicer. I use Cura, but also Simplify 3D is available. You can use a Prusa i3. I use a Monoprice 3, which is a Prusa clone, and do your flight simulation using MATLAB and Simulink. Coding is typically done with the Arduino type hardwares and C++, which is a version of Arduino code. I think almost everybody uses the Arduinos or the TPs or whatever other small Atmel type processors are out there. Don't know too many people that are using the larger computer systems and actual programming in real C++, using real C Visual Studio type tools, or real Visual C, which is editor type tool. But I'd recommend you take a look at something outside of Arduino, but Arduino is a typical starting point. Faster, and it loads as a single EEPROM type of having a hard drive or relying on a card. If you're going to print your own circuit boards, that's really getting more advanced up there. You use AutoCAD's Eagle program, and you can send those to China, and for a small price, they'll print those circuit boards for you. Test them. I expect to at some point see college students especially are using tools, but it's not beyond the capability of a middle schooler or a high schooler to be able to use PCB design tools, especially if you're interested in electronics or electric circuits. Have a mentor that can show you, or you just research it and you learn it out there on the internet. Lots of documentary, tremendous amounts of resources in terms of how to document it. If you're doing any iOS applications, you can use Xcode or Swift, or I'd recommend Android Studio is if you're going to do any web type designs on your smartphone, or typical Java to SmartPad. Okay, so we're getting through this as quick as I can. I promise it won't be too much longer. There's a lot to cover. You want to do a good recovery system design because most of the failures are in the recovery systems. They either fall apart, they don't release, it's too cold, you don't use enough baby powder on your parachute, and there's all kinds of things that can go wrong here. So talk to your mentor who has had some experience with rocket systems. That's why they're there. They'll tell you about all the failure modes and all the ways that typically result in launch failures or design failures. That's just ask their advice. Their experience matters most. The typical piston ejection is done with a piston coupler. You can learn how to do that again from videos. You can buy them. Think through how you want to deploy. Again, you don't do any dual deployment in TARC, but you could look at recovery systems that are controlled by your computer that dual deploy. Again, this area is wide open for how do you want to deploy parachutes using other than pyrotechnic charges. You can't use any pyrotechnic charges, but you could still use the same design approach using servos controlled with altitude barometers controlled by your flight computer. And there's no limit to the number of parachutes you could release at different times or different altitudes, again, depending on imagination and creativity, all in the name of learning how to build a more technical. Gains you some points in terms of the judges judging your marketing. Okay? It doesn't necessarily help you nail those altitudes anymore unless you've got it down to a science and you can really cut down the altitude release errors and timing errors that are typical caused by the ejection charges on the motors. The motors and their ejection charges are just not that precise, so you're dealing with a lot of variability no matter what if you're only on the ejection charge. So a lot of people are using speed brake systems to offset that, but they still can't predict when that charge goes off. Factor that you're going to have to use servos to get it. The shock absorber is again something I talked about before. Consider using a 24-inch nylon parachute. That's typically F-type TARC design parachute sizes. You want potentially one drogue type if you want to go down that road, or just a single parachute with shock cord. And I recommend you not use bungee. Use the Kevlar shock cord because it's stronger, and make sure it's long. Typically, you want it 5 times the length of your rocket. You can't ever get enough shock cord length. Some of the failures that happen with lines being taken. Systems that don't deploy, all kinds of. You can purchase your parachutes. Again, some people get 18-inch ones for the lighter, smaller rockets that are just over 650 millimeters in length, and any longer, bigger ones or heavier ones, as long as they don't go over 650 grams, you can handle the 24-inch recovery system. That slows your descent and lets you use smaller motors with less altitude. Don't do this. This is a BPS.Space's level 3 cert. I just wanted to share it. Bernard has got a wonderful capability going on out there. It's unfortunate he doesn't share much of that with the older community of NAR types of guys, although he did bring his what was it? Oh, his SpaceX Heavy, Falcon Heavy he brought in, showed everybody. defense. But that's the last I've seen him closely interacting with the NAR and the older members. He tends to design only with his own young group out there, but his level 3 certs didn't survive. Again, the reasons were he was going too fast at Mach speeds, kind of an overreach, didn't do enough modeling probably, and didn't get a strong enough parachute. And that's kind of a shame because I'm sure it was frustrating for him to deal with all that time and effort and work they put into it. But I highly recommend you go out and take a look at his systems. Again, it's bps.space, Joe Barnard, and he's paving the way for a lot of people to do the automated thrust vector control. I'm learning to catch up with him as quickly as I can and try to pass any knowledge I can on to you as TARC students and to my own colleagues that are in the NAR. As much as we can, building the larger systems, make our systems more complex and better designs, and keeps our own hobby more interesting. In fact, I'd like to see an adult version of TARC. Not more than just the S2. S2 is an international FAI competition against the globe that's TARC-like, but just within our own club and our own NAR competition, I'd like to see TARC-type bot competition more often with computer-controlled electronics being, again, the same design goal, keeps the sport more interesting. The interesting thing about this is most of these systems rely on prior knowledge and prior information, but the rocket community is ignoring a lot of the advancement that's been done by the drone community. One of the things that I'm personally taking on is try to educate my rocket companions on all the stuff out there that the drone community has done, specifically in the area of flight control dynamics and flight controllers and the various types of control theory loops that are being done. A lot that can be gained by using the PID controller systems out there that are typically done now. Even in the modeling airplane community is starting to pick up PID controllers that are created by one company or two companies. But the primary systems using advanced computer flight controllers and GPS type systems, drone community. Almost all of my design projects, I'm pulling all that technology over from drone technology and putting into, because it's just so cool. So many things you can do. And almost every rocket I build, I'm putting some type of drone technology. Make it more fascinating, sophisticated. In fact, I'm writing code for the rocket version of stuff that's being medical challenge group. So I'd recommend you take a look at some of the level 1, 2, 3 cert recovery systems. You're not authorized to use their motors, but a lot of their recovery designs are very complex and typically advanced. You just can't do dual deployment, but take a look at how they deploy and fold and deploy shot cords and things. A lot of good techniques out there that talking to people that have. Again, you'll see the mistakes that are made. Usually happens in level 3. Things get tangled, things get ejected too fast. You shouldn't have too many problems with that, though. It's F-size engines and using the normal systems. My goal is to go ahead and enter phase 2 of this, which is the testing phase. No, phase 2 is the actual build phase. I have all of my components ready. It's now the first part of March. Building my own system, going to the second phase of these documented videos, which will be the build process, and the third phase between March and April will be flight testing phase, a third documented TARC video that's put out. But currently I'm looking, again, you have to be in somewhere in the 80 Newton-second max allowable range. So I'm looking between 40 and 80 type Newton-second engines. Looks like my F-44W8 is a good candidate for a smaller rocket design, and the F-27-4 is a good indicator for the first model design I had. I'm not sure exactly yet which of those two I'm going to go with, and probably test both. Test more than just one design, more than just one type of rocket. Looking at your motor testing, again, you can only use the ones that are approved by TARC. Consider putting some design LEDs in it from your flight controller. It always looks cool to have blinking lights. Again, you'll learn a lot. Optimize your motor thrust for emission. And again, if you use speed brakes and a flight controller, you can start to nail that and even consider controlling the thrust. Done yet. Don't build any sugar motors. There's lots of stuff on the internet about how to do that, but don't do it unless you're in school, sanctioned by a college or a university with professors that are teaching you the chemistry and the technology of how to. Or you belong to, say, another club like Tripoli, where its goal is to use the high power systems and doing a high power certification out. Don't do any homemade or vegetable oil hybrids or potassium nitrate, potassium chloride binder type motors. Just buy the ones that you need, and they're most reliable and they're the safest, typically, that you can. Either Cesaroni, Airtech, or Estes motors, any of those major manufacturers. Great motors, great engines, but usually great reliability. Consider that black powder, if it's old, will get cracks and you'll get catastrophic failures. If you're trying to use old engines, don't. Composite motors typically don't have those kind of catastrophic failures, but they do have more failure modes than black powder in terms of when you buy them and build them your own. Reloadables have a special tendency to have catastrophic burn-throughs because you put the seals in the wrong place, you reverse the seals, forgot the fore or aft closures, or you did something wrong that allowed a seal to have a small amount of crack in it, have enough silicone, or you had too much silicone. All kinds of things go wrong there. It's a great deal of experience needed if you're going to do your own. I'd recommend that you test your motor if you have time, and that just means build yourself a test stand and do a firing, and I would fire it in the actual tube if you can, so that you can determine the strength of materials that are in. Don't forget your igniters. There are special types that you need. They typically motors. And make sure you order your engines early, because as they get closer and closer to April and May, I think the deadline is end of April for the last qualifying, and the contest is May. I think, get the date here in a minute, but I think it's 14. Don't hold me to that. And we'll see you at Big Meadows, hopefully, and you'll have all your engines, and sponsor or your school will make sure that you have enough. Don't forget the dual egg payload restrictions are horizontal. This is the apogee version of that foam container. Do not buy the vertical version. And remember that you are restricted in terms of the grams and weight and the length, 56 millimeters, which means that somebody's going to measure those eggs for you. Fortunately, you have to do it yourself, unless you don't have a mentor or a sponsor who is helping you along. They're not allowed to help you build anything. Just remember that. So you have to do all this stuff yourself. Again, this is the vertical version. Don't buy this one unless you're doing an NRC contest. Don't want that. Again, electronics, as a minimum, you have to have an altimeter. This is one way to put the altimeter in, and typically it's one of those 3 approved. It's one of the peanuts. Peanuts are very, very common. Recommend that you figure out how you're going to mount them. You can fly the Perfect Flight Peanut, the Perfect Firefly, or the APRA, which are cheaper version of the Peanut. And that standardization makes it easy. If you want to, while you're doing testing, add another altimeter just so you can compare the two. Adderall is a typical system out there that's very, very small and lightweight, and it's typically help you get knowledge required for contest rockets, because this is really the lightest weight system out there. It even has dual deployment capability or ejection capability. Later in another design with another system, use that. Just this is not approved for TARC and deployment or pyrotechnic approaches that the other altimeters use, and all for safety. But just take a look at that if you want to add it into your system. Sorry, need to take those couple of those videos out. I like these Jolly Logics a lot. You can add those in. They're not approved for TARC. Again, you can only use the 3 that are approved. But anything that lets you download data into the flight computer and then analyze it, I think is great. So you need to get the versions of either MicroPeak that will download your data, Ultra Adral that will download your data, or the version of Jolly Logic that into a computer. And that, I think, is helpful to actually see the altimeter-based profile, unless you have a GPS and altimeter built into your flight controller, which is very possible, and this is the one I use. It's one. I use it in a system that is already capable of all this, which is Mission Planner, and to my knowledge, nobody uses it. Wish they did. Nobody that I know of in a rocket did it except for me. So this is my contribution to you. So you're going to build a flight controller. Don't have to go out to Arduino and do all your programming and code on your own, although you will need to code differently than what's existing in the existing groups, because they're not designed for rockets. These systems were designed for airplanes and designed for drones. So I'm currently coding up the version of the larger rocket project that was started back in 2012 and didn't finish and got abandoned because they didn't design their code to a design standard that fit well with the whole open source community. So we're going to try to fix that problem, get a decent version of this software for rockets, but you can use the existing software and modify it as long as you don't do any thrust vector control. Use the GPS portion, set the parameters up to align it with servos and fire servers, all that kind of stuff. All works. You have to work with it and do some creative thinking about it. I personally would do both. Design an Arduino system and do the code, because you'll learn a lot from it. But I'd also take a look at these ArduPilot open source systems, copy it, and go further. Even Joe Bernard is not using this capability. Go further and catch up with the drone and airplane community using the as an advanced system. Don't forget your bill of materials. Learn a little about your IMUs, gyros, and accelerometers as you go. You can also look at battery systems and what are called BECS, battery elimination circuits, which is basically a voltage regulator. Have that possibly in your system. Again, all this electronics, I'd recommend you use receivers, transmitters for your servos and controllers, and flip a switch and eject your parachute with that. I think that that's permitted to have that kind of controller. We'll just have to check. The flight computers are committed, are allowed. You just can't have any active flight control. So you can flip a servo, I think, from a transmitter. I'll just have to check with that. Check with the Trip Barber. I don't think they prohibited you from using a receiver system to flip a servo and eject your parachute. I think that would be one system that worked. You can use S-Bus systems and FR-Sky type systems, or in my favorite is the Spectrum type radios and transceivers. Personally, they're going pretty far into remote type reliable Spectrum satellite controllers. All they get to, especially into drones, they're really so. Don't forget some of the telemetry radios are necessary to send GPS data back. I personally would recommend you consider looking at GPS additions. All these make your rocket heavier and they make it more complex. But if you're a team that's been building the same stuff for year after year and you've been doing 12 years, you should be at a point now where you can start considering these telemetry systems, downloading and collecting data and analyzing your data in your design phase. It won't help you necessarily win because there is some luck involved. But the tighter you can make those tolerances and the more you can get those launches, the closer to the absolutes, the more likely you'll have a chance of winning. Because the winning teams are typically going to be 8 to 10. Do that repeatedly over and over and over, you'll be in the top system. So telemetry could really help you, as well as keeping statistical data on your altitude minimum in a spreadsheet using statistics. Use your short-range telemetry. Here's a number of radios that are available. Pick radios of 3DR type components. I'd recommend those over all of them. The longer range ones are more expensive. RFD 900, very nice. Even Dragon Link, but those are heavy. So I'd go back to the SIK 3DR robotics type radios. upload system and a download system. All that and hook that up to your GPS. Typically, it hooks up to the UART portion. And if you really got time and your team is highly motivated, build yourself a ground station with tracking capability. There's just so many things you can go to learn, and more technology and more capability. If your team is as advanced as some of the ones that we've seen coming out now, that are starting to use flight computers, it wouldn't take you, a year or so to build these complex ground. And if possible, put some cameras in it. Systems are really simple and easy to use. Again, they just require a video transmitter and an OSD, which is on-screen display system, and then you have to have a display, or you can even use your VR goggles. Video receivers at 5 gigahertz frequency. So Foxeer is a good camera, RunCam's a good camera. I mean, there's just hundreds of good camera systems. The last thing I recommend is, if you have the capability, put yourself a safety switch into the system, especially if you're using a flight computer that's going to start your motors or whatever, which is possible. You can start a motor from countdown and all that other stuff is capable. You have to check with the TARC mentors, because there may be rules against firing your own motor with the flight computer, all right? So they typically want to fire those manually with the range control RSO person being the only person that can push that safety switch button. But if you wire up a safety switch to your electronics and your battery, and you just use that to turn it on and turn it off, or insert a safety flag, remove before flight, that really adds to the safety and sophistication of. That's the end of my video. I hope it was enjoyable. I hope it's something that's very educational, gets you down the road in terms of using your team's maximum capability and ability to think smart, think out of the box, be innovative, and get those processes and systems design concepts down that the TARC program is built for. I want you to learn as much as we can, and to do that, do as much research as you can, as much marketing, video learning as you can, and really impress those judges with you have a well-organized team. Works just like a SpaceX team or a Rocketdyne team or a ULA team. Just learn that what you learn can come from all sources. Don't restrict yourself to just people your own age or your whatever. Get out there and talk to people that have been in the rocket industry for a long time. They've got great ideas, and they sometimes will surprise you with how much they know and how much they can help, even if you assume they don't know anything, which is kind of typical. So just learn everything you can, do the research, get on the internet, talk to people, and get your organized team, go out there and win that contest.